Welcome to the fourth week of lecture for Unit 1 of the Introduction to Data Science module. This week we'll be beginning our lectures by discussing some of the basic data science modules within the Python data science stack. So if you open up this basic DS modules notebook in the data wrangling directory, the Python data science stack includes quite a few different packages. Some accomplish some more specific or complex tasks, while others provide broad basic functionality and are sort of the building blocks for subsequent packages and modules. We'll be beginning with one of the most fundamental packages in the Python data science stack, which is NumPy. NumPy, along with SciPy, are some of the older Python packages, still actively maintained and updated and improved, but it's a bit older than some of the other data science packages. And NumPy and SciPy were the tools that first made Python an attractive programming language to scientists in all kinds of disciplines in the first place. I first started using Python in my own scientific studies, and NumPy was one of the first things I ever used an import statement for. NumPy expands on built-in Python data structures and functions by offering, first of all, a number of mathematical functions that are a little more advanced than the built-in Python ones. So we get access to things like sine and cosine, logarithms, floor and ceiling, and exponentiation, a number of different mathematical functions. NumPy also has a excellent pseudo-random number generating submodule for when we need random numbers or to generate random samples from a data structure. And the most important component of NumPy is it introduces what's called the ndarray, standing for n-dimensional array. An array conceptually is similar to a n-dimensional matrix or tensor, for those of you who are familiar with those mathematical terms. We'll see that in Python, it bears a resemblance to working with lists of lists, where the depth of how many lists there are corresponds with the dimensions of the array. So here we have a two-dimensional array, and we could construct a similar object in Python by having a list of lists where each list is one row in this array. And we'll find shortly, by working through some examples, that the NumPy array works in a sort of similar fashion, but with a single flat data structure. And it's highly optimized for doing mathematical computations compared to Python lists. And we'll discuss more of that later in the lecture as well. So since a NumPy array is n-dimensional, it could be one-dimensional, like this, two-dimensional, like we have up here, three-dimensional, if this were to somehow go into the screen, if we had a depth, and then we would have three numbers indexing each element of the array, the row, the column, and the depth. And it could be 4 dimensions, 5 dimensions, any number, as many as we want. Such arrays are often used for representing images, in which case they are 2-dimensional, of course. And for a color image, we might have a 3D array, where the third image are the red, green, and blue color channels. So let's work through some examples comparing this NumPy array to lists. So to use any of the objects or functions defined in NumPy, we'll have to, of course, import it. NumPy is not part of the Python standard library. If you were installing Python on your own machine and creating your own Python environment, you would have to install NumPy into that environment using a Python package manager like conda or pip. But we've already set up your environment on the Jupyter Hub to have NumPy installed, so we can just go ahead and import that. And if we wanted to make a 2-dimensional array using built-in Python data structures like lists, as I mentioned before, we could make a list of lists where each inner list we interpret as a different row of the matrix. So there we have our list of lists. And we could turn that into a NumPy array by simply passing that list of lists into the NumPy array function. And that will return us an ndarray object. So we see this is a NumPy nd array. And this also looks like a list of lists. That's its visual representation, is a list of lists. And they're formatted a little differently, but they look pretty similar so far. But they are very different kinds of objects, as we will shortly see. One distinguishing attribute is a NumPy array has a shape given by the size of its dimensions. So this is in contrast with lists, which have no definite shape, say. So it's not a problem, for instance, to define some non-rectangular object as a list of lists. So we could have a list of lists where each inner list is a different length. Not an issue. But what happens when we try and turn this list of lists into a NumPy array is now we get a array with 3 elements, and each element is a list. Now this is a really different situation from what we had up here, where we ended up with a 3 by 3 array. NumPy arrays must be rectangular. They must have in each row the same number of elements, in each column the same number of elements. When NumPy tries to interpret this list of lists, it says, okay, the first row has 2 elements, the second row has 3 elements, the fourth row has 4 elements. Well, that's not a rectangular shape. I can't coerce that into being a rectangle. So I'm going to do the next best thing and assume that each of these lists is itself a single object. And so instead of having a array where each of these lists gets broken into rows, I have an array just with 3 elements. and it's one-dimensional rather than two-dimensional. That's the only way NumPy knows how to deal with this situation. And as I mentioned, this is related to the idea that an array has a shape. So our first array, as I mentioned, is 3 by 3. 3 elements in each row, 3 elements in each column. It's the size of the dimensions of each dimension of the array. 3 elements in the first dimension, 3 elements in the second dimension. The non-rectangular array, on the other hand, has a shape of 3, comma, nothing. This comma nothing indicates to us that this is a one-dimensional array. And that single dimension has 3 elements in it. We can notice another difference, which is arrays have a data type. So in addition to arrays requiring a rectangular shape, they also require a homogeneous data type. This is in contrast with lists. In lists, we could store strings and numbers and Boolean values all together, or even lists and tuples and other data structures, without suffering any kind of penalty or without the list becoming a little strange. NumPy arrays are the first example we've encountered of a homogeneous data structure, or a data structure with homogeneous data type. So an array, this one that we encountered above, has a data type, dtype, of int64. Each element is an integer with 64 bits of memory dedicated to storing that number. The non-rectangular array has a data type object. Object is a catch-all data type for representing things that are not numbers or strings or Boolean values. Anytime we have a data structure stored in a NumPy array, that NumPy array will have data type object. Anytime we have mixed types in a NumPy array, that array will have a data type of object. So for example, if I try to make an array with different types of data in it, I can do it, it's not a problem. But the data type, well, here it's not object, but it's something a little bit strange. Yeah, so this might as well be object. This is actually a statement of how much memory is being allocated for each element. But in general, if we have mixed types, we would expect this data type to be object. And in fact, most of the time that we're working with NumPy arrays, we'll want a data type that is either Boolean, int of some type, or a float of some type. If we have a data type that's outside of those options, probably we're better suited by working with a different kind of data structure, because we won't be able to take advantage of the optimized code behind the NumPy array for performing calculations. So I'm going to stop the video here and move on to the next video. So this has been a short introduction to the idea of NumPy arrays. They are a ordered, mutable, homogeneous data structure. So similar to lists, except that they have homogeneous data type, and we also see that they have a shape. They must be rectangular, meaning each row or each column or each level along any particular dimension must have uniform size. In the next video, we'll talk about some other ways to create arrays.